Good day, everybody. In today's lecture, we'll be going over the electronic configuration and how it can be used to explain the periodic table in terms of the element's properties and changes it can undergo. Previously, we have learned the brief history of the atomic theory development. For example, we learned that atoms are made of three different components: protons, neutrons, and electrons. If you still recall, in this process, we actually learned a couple of atomic models. The first one is plum-pudding model, proposed by J.J. Thomson. And this model turns out to be wrong. It was replaced by the nuclear model, which was proposed by Ernest Rutherford, based on the unexpected results from the gold foil experiment. In this nuclear model, the protons and neutrons form the nucleus, which is extremely small, at the center of the atom, with the electrons moving in the mostly open space. But it never tells us how the electrons are actually moving or how they are arranged in the mostly open space. In today's lecture, we will go into the details how the electrons are actually arranged by talking about the electronic configuration, and upon the completion of this lecture, you'll have more understanding about why some elements are more reactive and some are very unreactive toward chemical reactions. For example, these days, we do know hydrogen is highly reactive, but we didn't know a long time ago, and we paid a heavy price for that. In 1937, while landing in New Jersey on its first transatlantic crossing, the Hindenburg burst into flames, destroying the airship and killing 36 of the 97 passengers. The filling gas, hydrogen gas, was ignited, resulting in an explosion and destroyed the airship. Modern blimps or balloons are almost always filled with helium because helium atom has two protons and two electrons. It's a very, very stable configuration. Helium is very unreactive. In this chapter, we'll learn about the models that explain why helium is very stable and has very low reactivity. In this chapter, we'll study two important models. The first is the Bohr's atomic model, and the second is the so-called quantum mechanical model. And we'll try to explain why some elements are more reactive than others. We'll study how the electrons exist in atoms and how those electrons affect the chemical and physical properties of elements. In the development of quantum mechanics, many scientists have made great contributions. For example, Niels Bohr, Erwin Schrödinger, along with Albert Einstein. And this theory hinges on one important property. It's so-called wave-particle duality. So what is the so-called wave-particle duality? It basically tells you a wave can not only behave like a wave, like light, it can behave like a wave, but can also behave like a particle. Conversely, a particle like an electron can not only behave like a particle, it can also behave like a wave. Let's first look into the duality of light, which tells you light can behave both like a wave and a particle. Light is a form of electromagnetic radiation. It behaves like a wave. There is no doubt about it. It's well established light can behave like a wave. A wave would have several characteristics, such as wavelength and frequency. When you look at this picture, the distance between the neighboring peaks or troughs is so-called wavelength, and the frequency tells you how many waves have passed by. in 1 second. Please note wave and frequency are inversely related, or the shorter the wavelength, the higher the frequency. The quantitative relationship between wavelength and frequency is the speed of light c is the wavelength times frequency, which is written as nu. This nu looks like a v, but v is like this. That's not a nu. That's and frequency is like a nu. There are many different types of light. For example, gamma rays, X-rays, UV light, visible light, IR or infrared, microwave, and the radio waves. Please pay attention to the relative wavelength, relative energy, and the relative frequency. As you notice over the top, the wavelength, on the right side, gamma ray has the shortest wavelength, but the highest frequency and the highest energy. Radio wave has the longest wavelength and the lowest frequency and the lowest energy. Visible light is a very, very small portion of the electromagnetic spectrum, as expanded as you can see over here. Let's look into the details about different colors of light. There are 7 major different colors: red, orange, yellow, green, blue, indigo, and violet, or Roygbev. When the light is passed through a prism, they are separated into different colors. Red light has a wavelength of about 750 nanometer, and the shortest wavelength, the violet or purple light, has a wavelength of about 400 nanometer. So our eyes can only see about 350 to 400 nanometer range of light, which is a very, very small range of wavelengths. So far, we have explored some key features of a wave nature of light. For example, frequency, wavelength. What about the particle nature of light? In the very beginning, we emphasized the wave particle nature of light is one of the foundation for quantum mechanics. So let's look at that aspect as well. Light can behave like particles. This has been proven by so-called photoelectric effect, which was explained using quantum theory by Albert Einstein. Basically, what this tells you is light can be viewed as a stream of particles that are called photons, and we can think of photon as a single packet of light energy. The amount of energy carried in the packet depends on the wavelength of the light. The shorter the wavelength, the greater the energy. The energy of light can be calculated by E equals h, which is Planck's constant, times c over lambda. Or, because c over lambda is actual frequency, E equals h times nu, h times frequency. So, the higher the frequency, the higher the energy. The longer the wavelength, the smaller the energy that light has. Let's work on a few examples. Arrange the 3 types for electromagnetic radiation or light: visible light, X-rays, and microwave in the order of increasing wavelength. We must be 100% clear about the relative wavelength, relative frequency, and the relative energy for the 7 different types of electromagnetic radiation. So let's start working on the first one. For wavelength, We do know microwave has the longest wavelength, and visible light is right in the middle. X-ray has the shortest wavelength. So we arrange it in the increasing wavelength. It will be X-ray, smaller wavelength than visible light, then microwave. Okay. The frequency is inversely proportional to wavelength, so the order will be the opposite. With microwave having the lowest frequency, then visible light in the middle, X-ray having the highest frequency. Okay. Remember, energy per photon can be calculated by E equals h times nu. So the higher the frequency, the higher the energy for each photon. So it's exactly the same order as B. It's microwave has the lowest energy out of three, visible light right in the middle, and the X-ray has the highest energy. A packet of light is called a what? A packet of light energy or particle of light is called a photon. So basically, what is a photon? A photon is a packet of energy or a packet of light energy or a particle of light. How are frequency and wavelength of light related? They are inversely proportional to each other. So the larger the wavelength, the smaller the frequency. The higher the frequency, the smaller the wavelength, which is exactly the same, because they are inversely related to each other. Next question. In which of the following are the types of electromagnetic radiation arranged in the order of increasing frequency? Again, I would like to emphasize you must know the relative frequency, wavelength, and energy for the 7 different types of electromagnetic radiation, also the 7 different colors of visible light. So let's look at that. Which of the following has the highest frequency? Apparently gamma ray has the highest frequency. When you look at that, hey, only answer C has gamma ray as the highest frequency. So radio wave has the longest wavelength, but the smallest frequency or lowest frequency. So C is the correct answer. Which color of visible light has the least energy per photon? Least energy means means the lowest frequency and the longest wavelength. So which light has the longest wavelength? Red light has the longest wavelength of about 750 nanometer. Violet has the shortest wavelength, thus the highest frequency and highest energy per photon. Let's summarize what we have learned so far. First, light is a type of electromagnetic radiation, and we have 7 different types EM waves. And you need to know the relative frequency, wavelength, and energy. Not only for the 7 different types of electromagnetic radiation, also for the 7 different colors of visible light. And 2 equations you also need to remember. The speed of light is frequency is the wavelength times frequency of the light. And second equation is h times nu will give you energy for that light, because nu can be calculated as C over lambda. So E can also be expressed by h times C over lambda. Another aspect of light is that light can behave like particles. This was proven by the photoelectric effect and explained by Albert Einstein. A photon is simply a packet of energy. In conclusion, light behaves like a wave and a particle. In the early 19th century, there's one phenomenon that puzzled the scientists, that is the emission spectrum of light. Here's some examples. The first one, you look at the light emitted from neon glass tube. And the second one is the light emitted from the mercury lamp. And the third one is light from the hydrogen lamp. You'll probably run into this when you do the experiment in your laboratory. Basically what happened is, when the light is emitted, they can actually run through a prism and be separated into different colors. But one distinctive characteristic for the emission spectra is, rather than what you see for the white light, as you can see over the top, this is continuous light. You see almost all wavelength of the light. But for the emission spectrum, you only see certain wavelengths of the light being emitted. For example, for hydrogen, in the visible light region, you only see 4 different wavelengths. 1, 2, 3, 4. It's very similar. You only see a few wavelengths of light for helium and neon light as well. Here's how you actually run the light through the prism and get them separated. Once you calibrate the separated light, then you have the wavelength for each emitted light. Bohr was the first person who perfectly explained the hydrogen emission spectrum. In Bohr's atomic model, he proposed the electrons can only exist in certain energy state. What he proposed was that energy is not continuous. The electrons can only exist in the orbits with certain amount of energy, and you cannot have more or a little bit more, a little bit less than that. Those states do not exist. Just like a ladder of energy states, you cannot just have states in between the steps. For each of the orbit, Bohr give it a quantum number like 1, 2, 3. And when the hydrogen atom absorbs energy and the electron is excited to higher energy state or higher energy orbit, then electrons, when it goes back to lower energy state, it emits a photon of light. So let's go into this details a little bit more. I want you to look at the right side of the slide. You have the nucleus sitting right in the middle. Then the electrons are going to be sitting in any of those circular orbits over there. N equals 1 means it's the lowest energy state, and we call that ground state. N equals 2 has higher energy. N equals 3 orbit would have even higher energy, and etc. You also notice that the distance between different orbits actually becomes bigger and bigger. However, the energy for those orbits, look at the left side. For n equals 1, it has the lowest energy. N equals 2, a little bit higher. N equals 3, 4, 5, 6, they're even higher. But notice the spacing between the energy is becoming smaller. The gap between the energy states are becoming smaller. Do you remember we just mentioned the distance between different orbitals from n to 1 to 2 to 3 to 4, the distance between the orbits are becoming bigger and bigger. However, the energy gap or the difference between the neighboring energy states for the energy difference between 1 and 2, between 2 and 3, between 3 and 4, the energy gap is becoming smaller and smaller. For hydrogen, the lowest energy state will be, let me write it this way, let's say that's n equals 1. All right, you have one electron sitting over there. Then when it receives external energy, for example, from electricity or from heat, then it will jump to higher energy state. Because now you possess more energy, you cannot stay in the low energy orbit. So it goes to, for example, it might go to 2, you might go to n equals 3, or you might go to n equals 4. All right, you might go to any of this depending on how much energy you absorb. But to remember, higher energy orbits have more energy, and those states are so-called excited states. It's less stable. So the electrons would like to release the extra energy they have absorbed. So what they are going to do is now you are in the one of the higher energy state. So for example, if you started with number 4, all right, now you have way more energy than the ground state. You would like to go to lower energy state to release extra energy and become more stable. You can also go to number 2, or you can go back to the ground state, n equals number 1. In this process, when you absorb energy, and you will see that's so-called absorption. When you go from higher energy orbits to lower energy orbits, that's called emission. If you measure the wavelength for the emitted light, you will be able to see what we just observed in previous slides. Let's summarize this for one more time. First, the energy of the absorbed light or emitted light, they have certain energy, so they correspond to different wavelength or frequency. Second, the light emitted by the so-called excited atoms, which contains the electrons in the excited state or higher energy state. In the case of hydrogen spectrum, the electron, excited electron, if you jump from orbit n equals 3 back to n equals 2, it gives you a light that has a wavelength of 657 nanometer, which corresponds to the red light you see. And if you jump from n equals 4, from 4 to 2, that gives you the blue-green light. And the purple light comes from the jumping from 5 to 2, which release energy. So Bohr's model perfectly explained the hydrogen spectrum, and for this reason, he won the Nobel Prize. However, Bohr's model cannot explain any emission spectrum for elements that contained more than one electron. For these reasons, Bohr's model was replaced with a more complicated model, which is called quantum mechanics. In quantum mechanics, the orbits in Bohr's model are replaced with the quantum mechanical orbitals. So what's the difference between the orbits and the orbitals? The orbits are just like the orbits for the planets surrounding the stars. You can predict exactly when and where the planet is. So in Bohr's model, you should be able to predict when and where exactly that electron is. However, in the quantum mechanical model, you cannot predict when and where you can find that electron. Rather, in these orbitals in the quantum mechanical model, you can only predict the chance or what probability you can see certain electron in a certain place. In other words, an orbital in the quantum mechanics only represent the probability map that shows you where an electron can be found. In the quantum mechanics model, I want you to pay attention to several things. First, you have so-called principal quantum number. Principal quantum number represents shell. For example, n equals 1, we can say it's shell number 1. Similarly, n equals 2, we can call that shell number 2, shell number 3, etc. And the second thing is a letter. We'll use a letter to indicate so-called a subshell. A letter to indicate a subshell. For example, S, we call that S subshell. P, we can call that P subshell. D subshell, and F subshells. And inside the subshell, we have orbitals inside. Each subshell has certain number of orbitals. For example, in S subshell, you only have one orbital inside. Number of orbitals. Okay. Then for P subshell, you have 3 orbitals inside. D, 5, F, and 7. F has 7 orbitals inside. All right. And inside the orbitals, we have electrons. Let's put everything together for one more time. N, the principal quantum number, represents the shell. You have different numbers of shells. Inside the shell reside the subshells. Inside the subshell, you have orbitals. Inside orbitals, you will see the electrons. So N represents shell. Then the letters represent the subshell. So you have S subshell, P subshell, D, F, etc. If you put the number and the letter together, it specifies a subshell. For example, you might have a 1S subshell, 2S subshell, 3S subshell. They are all S subshells, but they are in different shells. Okay. You also have P subshell, 2P, 3P, 4P, etc. We'll go into the details how that works in a little bit. Another concept which we mentioned briefly when we talk about the Bohr's model. In quantum mechanics model, we also have so-called ground state, which tells you it's the lowest energy state. Excited state, it's the energy state that is higher than the lowest possible. So the higher energy state is called excited state. Principal quantum numbers is very similar to what we just saw in the Bohr's model. It's the positive whole numbers like a 1, 2, 3, 4. On the right side of this slide, as we can see, it represents the energy for n equals 1, 2, 3. Notice the energy gap between the neighboring lines are becoming smaller and smaller, which is also similar to Bohr's model. But do remember, the major difference is in Bohr's model, you have orbitals and, in Bohr's model, you have orbits. In quantum mechanics, you have orbitals. And do remember, orbitals are the probability map, showing you the probability where you can find an electron. So one more time, principal quantum numbers are positive whole numbers 1, 2, 3, 4, etc. And the principal quantum number by itself represents one thing, that is shell. And the letters S, P, D, F, etc. You can actually have G, H, but in our periodic table, these are the only 4 subshells that we will use. We don't write any other letters, not because they don't exist, it's because we don't need to use it in the periodic table. For the subshell, we use letters to represent it, and all orbitals inside each subshell, they have different kinds of shapes. For example, S orbitals, P orbitals, D orbitals, F orbitals, they all have different shapes. So when you look at S orbitals, we have 2 different ways to represent it. On the left side, this is so-called a dot representation. The denser the dots you see, the more probable for you to find one electron over there. We can also use so-called shape representation to tell you the chance to find where you can find an electron. When you superimpose both of them, you notice that in the shape representation, it does not include all probability to find the electron. In other words, outside that sphere, as you see in this shape representation, you still have some chance. Look at that, outside that sphere, you still have chances to find electrons. But that sphere or the shape representation would include 90% of the chance to find the electrons. So s orbitals, they are spherical shape. Let's look at the p orbitals and d orbitals. Okay, when you look at p orbitals, it's just like you tie up two balloons together. All right, so it looks like a dumbbell shape. In p, as we mentioned, all p subshell will have three different orbitals. So you have 1, 2, 3 different orbitals inside. Okay, and z has 5 orbitals inside with different orientations. 1, 2, 3, 4, 5 over here. And one of the d orbitals, it looks slightly different from all others. It's like a donut with the dumbbell when you look at the last one. All right, f orbitals, most likely it's like 8 balloons tied together, but we're not going to look at the shape of f orbitals for now. One more thing I want to emphasize is s orbitals all look the same. They are spherical in shape, but you look at compare 1s and 2s orbitals. Okay, 1s and 2s have the same shape, but the size for 2s is bigger than that of a 1s. All right, so let's go on and work on some problems. So what is the shape of p orbitals? Yeah, it's donut shape. Spherical shape is for s orbitals. Okay. Now let's look at how many subshells you have in each shell. Remember, the principal quantum number, like 1, 2, 3, 4, etc., represents the shell. So in this shell number 1, you have a s subshell. Okay, and in shell number 2, you have both s and p subshells. And it's written over here using boxes. We call this orbital diagrams. And in 3, you would have 3 different types of subshells, S, P, and D. N equals 4, you have 4 different types. N equals 5, you would expect to have 5 different subshells. So if you combine this number and letter together, we can say in shell number 1, you have 1 S subshell only. In shell number 2, you have 2s and 2p subshell. All right. Now for shell number 3, you have 3s subshell, 3p subshell, okay, 3s, 3p, and 3d subshell. Okay. Then you have 4s, 4p, 4d, 4f, etc. Okay. Hey, notice we also mentioned one thing. Inside the subshells, you have orbitals. In each s subshell, how many orbitals? Do you still remember? S, P, D, F. Let's quickly review this. How many orbitals do you have? The number, I just cannot write it in this here. So number of orbitals in S is 1, P you have 3, D 5, F 7. So if you want to represent the details about how many orbitals in each subshell, you can write it slightly differently, like what you see over here. All right. Over here you have more details. In S subshell, you use the lines to represent the subshells and orbitals, because S subshells only has one orbital, so use one line to represent it. So you have 1s, which has lower energy than 2s. Okay, 2s has lower energy than p subshell. Do you remember each p subshell has how many orbitals? 3 orbitals. That's why you use 1, 2, 3, 3 different lines to represent it. Similarly, you have 3s, then you have 3p, which has 3 orbitals. Now, if you look at the d orbitals, all right, you look at d orbitals. 1, 2, 3, 4, 5. Did you see that? Because d subshell has 5 orbitals. Let's move on. Remember, inside the subshell, you have orbitals. Inside the orbitals, you have electrons. If we can write a symbol that represents the electrons in the subshell or in the orbitals of the subshell, then we can call this electronic configuration, as you can see over here. For example, hydrogen has 1 electron. Then you put that 1 electron in the lowest energy state, which is 1s. S has 1 orbital inside, and hydrogen has 1 electron. So you simply put that 1 electron as the superscript. So the first one you see over here, this one is principal quantum number. Principal quantum number, Qn, okay? And the S, it tells you where in that shell the electron is. So that's the subshell. S is the subshell, okay? Now 1, it tells you the number of electrons inside that particular orbital in that subshell, okay? All right. We can also write this slightly different way. For example, we can use orbital diagram to represent it, using boxes or lines to represent it, okay? All right, you have 1 electron. You use a single-headed arrow to represent the electron. So inside 1, you use, that's your 1s, you use a box to represent it. You have 1 electron inside, you can put 1 arrow inside, okay? Let's quickly summarize everything we just talked about, because this is really, really important. First, a principal quantum number represents a shell, and a letter represents a subshell, okay? And in shell number 1, you have 1 possible subshell, which is 1s. In 2, you have 2 possibilities, 3 possibilities, 4 possibilities. And in 1, you would have 1s. In 2, you have 2 possibilities, 2s and 2p. In 3, you would have 3s, 3p, and 3d. In 4, you would have 4s, 4p, 4d, and 4f. And 5, you would have 5s, 5p, 5d, 5f. You would have 1 more. We actually use 5g to represent it. But as I mentioned already, we usually don't write 5g, not because 5g does not exist. It does exist, but we don't get to use it in our 118 periodic table. So a lot of times, starting from the 5th shell, we don't write anything higher than f. For example, this one, a lot of times we don't write it, okay? So with this, we are almost ready. Another thing we emphasized is for each subshell, we should know how many orbitals are inside. Any S subshell, like 1s, 2s, or 4s, each S subshell would have 1 orbital inside. P would have 3, D, 5, F, and 7. All right, now we are ready to do the electronic configuration. Almost ready, all right? So you might be asking one natural question. Now we know how many subshells we have. Now we also know in each subshell how many orbitals you have, but how many electrons can you put in 1 orbital? The answer is done by Pauli's Pauli exclusion principle, which tells you only 2 maximum number of electrons can be in 1 orbital. So that's Pauli exclusion principle. Not only you can have 2 max, those 2 electrons in the same orbital, must have opposing spins. For example, if I use this box to represent one orbital, if I put one electron in, spinning up, then the next electron, you cannot spin up because that's wrong. Pauli exclusion principle tells you if one spin up, the other one, if you want to put it in, it would be spin down. If you put 3 electrons in, that's impossible. Then you put a third one. That's also a violation of a Pauli exclusion principle. All right. Another rule you need to know, and we will go into details later on using example, is so-called Hund's rule. Hund's rule tells you when orbitals of identical energy are available, then the electrons will occupy the orbitals singly first with parallel spins or the same spins, okay, before you pairing up. That's so-called Hund's rule, right? So with all these rules, look at the previous slide for one more time, okay, and this slide. With all this information, we are ready to do the electronic configuration. But before we do that, let's have a look at a few questions to solidify what we have just learned. How many orbitals are associated with the given set of d orbitals? Okay, what do you mean given set of d orbitals? D orbitals are in d subshell. So it's asking you in d subshell, how many orbitals can you have? It's the same way. A set of orbitals, d orbitals, is the same as d subshell. So d has how many? Remember, s has 1 orbital, p has 3, d has 5. F would give you 7. All right. Next question. What's the maximum number of electrons allowed in F orbital? Remember, F subshell or F orbitals or F subshell, that's the same, all right? So so let's clarify something though, okay? Remember, F orbitals, a set of orbitals, okay, a set of F orbitals, that means it's a set F subshell, okay? F subshell has 7 orbitals inside. But do remember, this question does not ask you the set of orbitals. Actually, it's asking you in each F orbital, how many electrons can you have? In each F orbital, it must be 2 electrons. Actually, in any orbital, you can only have 2 maximum electrons. But in the set of F orbitals, or in F subshell, which has 7 electrons, you would be able to do 14 electrons in F subshell. But for each F orbital, you can only take 2 electrons, okay? So that's why 2 is the correct answer rather than 14. We need to understand the question. Next question. What's the maximum number of electrons in n equals 4 principal energy level? Hey, how many electrons can reside in n equals 4? Here you have a slightly different way to describe it. Principal energy level. Principal energy level is the same as the principal shell, or simply you call that a shell, or n equals 4, shell number 4. Hey, remember, in 4 we have 4s, 4p, 4d, and 4f. How many orbitals do you have? For each one, you have 1, 3, 5, and 7 orbitals. How many electrons can you take? Each orbital can have 2 electrons. So you have 2, 6, 10, 14. Hey, how many total electrons can you take in shell number 4? Or you would have to add all electrons together. When you add this together, okay, how many electrons can you take? This will give you 32 electrons. Okay, so that's actually what you see over here. All right. Okay, now let's move on and talk about how to do the electronic configuration, or in other words, how to put the electrons in the subshells. Let's do this. Helium has 2 electrons, so remember the electrons will fill in the lowest energy state first, one by one, before you fill in the next one. All right, so 1s is the lowest. So you basically can write the whole thing like the first one 1s, then you have a 2s, 2p, then you have 3s, 3p, etc. Okay, all right. But for helium, you only got 2 electrons. Why? Because the atomic number, when you look at your periodic table, it has 2 protons. The atomic number is number 2. To balance out the number of protons, you would have same number of electrons. That's why you have 2 electrons over here. So you put it in 1s2. All right. What about lithium? Lithium has 3 electrons. Oh, you might be thinking, oh, that's easy. 1s3. No, that's wrong, because S subshell only has 1 orbital inside, which means you can only take 2 maximum electrons. You cannot do 1s2, 1s3. So after you put 2 electrons in, you have to put the extra electron in the next lowest energy. So that would be 2s. So you have 1 less left. Again, you can also represent these configuration using orbital diagram, like what you see over here. 2 oppositely spinning electrons. Okay, so one for the lithium, it's similar. 1s, you have 2 electrons, and the 2s, you have 1 electron inside. Of course, for the spin in the 2s, you can also put it as spin down. It doesn't matter. Now let's look at the carbon, which is slightly different. Remember, if we write the electronic configuration, you can simply write it. For example, you're going to fill in 1s. S subshell can only take 2 electrons, okay, and 2s2, because you cannot take more in S subshell. It's 2 maximum. Now in 2p, you can take 2 electrons for sure. Why? Because p has how many orbitals inside? 3 orbitals inside. Okay, so you can take 6 electrons. Okay, 6 electrons maximum. So you only have 2. That's good. But if you want to use the orbital diagram to represent it, you got to be careful. Okay, 1s opposite spinning, opposite spins over here, 2s, and when you do 2p, you have 3 orbitals. Each box is used to represent one orbital. Okay, you have 3 orbitals. You're going to write 3 boxes together. So you fill in the first electron, then you're going to fill in the next. For the next electron, you don't want to put inside the same box as the first one, because as we learned for Hund's rule, it tells you when filling the orbitals with the same energy, all of this p orbitals have the same energy. So what you're going to do is you fill in the first one, as you see over here, then you're going to spread out before you're pairing up. So the next one would be like this. Okay, let's actually look at more examples so you know what I'm talking about. For example, for nitrogen, you have 7 electrons. Electronic configuration using subshells, that's easy. Orbital diagram, you fill in 1s, 2s, and for all 3 electrons in the p orbitals, you spread out and spin in the same direction. Did you see that? That's Hund's rule. Now, if you have more electrons, like you see, you can write it as a 2p4, because you have a 1s2, that's 2 electrons. You have 6 more, now you have 4 more. Those 4 can be left in the p subshell. All right. So basically, if you do this stepwise, let me do this stepwise. So that's my 1s. You have 2 electrons inside. You have a 2s. You have 2 electrons inside. Now for the p orbitals, again, how many are left? You have 4 more, right? You're going to do it this way. I want you to look carefully. 1, 2, 3. Now you have occupied all the p orbitals. So you will have to start pairing up now. So the 4th one, you pair it up. Okay? So for fluorine, then the next one got paired up. And for neon, the last p orbital is paired up. Okay? So that's how this works. It's kind of very straightforward. Let's do maybe one more example. For example, we're going to do let's do sulfur. Look at your periodic table. You always keep one periodic table printed and handy. So look at your periodic table. You know sulfur has 16 protons. That's 16 electrons as well. So you're going to do a 1s2, 2s2, 2p. Oh, 2p can only take how many? P can only take 6 maximum. So now you have how many left? This is a 2 plus 2 plus 6. That's 10. You have 6 left. Okay. So 3s2. Now you have 4 left. Those 4 would be left in 3p. Okay. All right. So when you do this, if you do the diagram, you can also do the stepwise. 1s, 2s, 2p. So 1s, you have 2 electrons inside. You have 2s, 2 electrons inside. Do remember p has 3 orbitals inside. Let me rewrite this thing. Okay. So p, now you're going to do, this is 2p. Now you have 3s. Again, s has only 1 orbital, or you use 1 box to represent it. Now you have a 3p. Again, p has how many orbitals? 3, so use 3 boxes connected together to represent it. Have 3p. You have 4 electrons. You're going to fill singly first, then you pair this up. So when you look at the 3p4, right, that tells you have how many unpaired electrons. So here, when you look at that, that's 2 unpaired electrons. Okay, 2 unpaired electrons. Okay, so when you look at the nitrogen, look at this example, it would be 3 unpaired electrons, right? Let's work on another example. This will give you a complete idea of how to do electronic configuration. So look at the selenium. When you look at selenium, again, look at your periodic table so you know how many electrons selenium has. In your periodic table, you found out that selenium has 34 electrons. Okay, so you can do that. You might be thinking like, oh, that's easy. Now I know how to do it. So it's 1s2, 2s2, 2p6, 3s2, 3s, now a 3p6. Then you're going to naturally think, oh, 3d10. Oh, when you fill it this way, that's actually the wrong way to do it. Because actually, it turns out you don't fill 3d after 3p. You fill 4s first. Because 3d has slightly higher energy than 4s. Then you might be wondering, what? So how do I know which one to fill first? Is this just the one exception, or there are many exceptions? Actually, we don't call this exceptions. Okay, so we have one way to help you decide which one goes first. So if you write the orbitals, like what you did, like the right side, okay? So basically, you have you write for shell number 1, you have 1s inside. Then number 2, you have 2s and 2p. Number 3, shell number 3, SPD, then SPDF for shell number 4. And the shell number 5, you would have SPD and the F and the G. But as I mentioned, because we never get to use G, that's why we don't write a G over there. It's not because we don't have it. We do have it, okay? So what you're going to do is you do the arrow from top right to left bottom. Whichever goes through the arrow first will be having lower energy. So for example, the first one, you go through 1s, then you do another diagonal arrow from top right to left bottom. So next is 2s, then you go through 2p. Notice that? Let me use maybe different colors so you can see that. It's okay, yeah. Now the next one, you go this diagonal, then you keep going. Did you see that? That's how you do it. Okay, we can do a small demonstration of your 1s, then you have 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, then the 5s, 5p, 5d, 5f, okay, etc. So you go from top to right to left bottom, layer by layer. That's how you do it. You see that? You can keep going. Okay, now you have 6s, 6p, etc. So you just keep going so you know which one will go through there first. You see that? That's how you get the right side. Okay? All right. Let's work on a few more examples to solidify what we just learned. What is the configuration for P3 minus? Remember, when you look at a P3 minus, you have P3 minus. How many electrons do you have in P? Right. So you look at P, it has 15, but do remember, a 3 minus means you have gained 3 electrons. So that's 18 electrons you have. Okay. So how do you do 18? 1s2, 2s2, 2p6, 3s2, 3p, oh, 6. Oh, that's 18. That's 18 electrons. Okay. But when you look at all the choices, oh man, I don't see any one of those. So what happened? Okay. So basically, we have another way to represent electronic configuration. As you can see over here, we have something in brackets like this. Okay, so if you look at your periodic table, we can use the previous row. Remember, use previous row noble gas electronic configuration to represent electronic configuration. Okay, to represent so-called co-electrons. Okay, yeah, we're going to explain that in a little bit later on. Okay, so basically, when you look at this portion of that, that's exactly the same as neon, which has 10 electrons. So that's why if you rewrite it, this becomes the same as neon, 3s2, 3p6. Okay, this is so-called abbreviated electronic configuration, which makes the writing a little bit easier. You always use the previous row noble gas electronic configuration in the bracket to represent a portion of the complete electronic configuration. Then you have the abbreviated form. So for this reason, the correct answer would be B is the correct answer. Look at another one. What is the electronic configuration for copper ion? Okay, this one is kind of special. I'm going to introduce to you a new concept. For copper ion, when you write it, so copper has 29 electrons. Okay, so when you write this thing, it might be a 1s2, 2s2, 2p6, 3s2, 3p6. All right. Now the next one, still remember, do we go by 3D or do we go by 4s? Oh, we go by 4s first. If you don't remember, write that diagram as you see over here. All right, on the right side. Okay, write this diagram, then you will know which one goes first. So it turns out it's 4s first because 4s has lower energy than 3D. So it's 4s2. Now you have a 3d9. So it looks like, because we do know this first portion is neon, so looks like you might pick B as the correct answer, but this one turns out to be wrong. Theoretically, you should get B as the correct answer, as we see over here. However, we have a special rule that involves over here. When you have d orbitals, remember d orbitals D subshells has 5 orbitals inside, which can take 10 electrons maximum. So 9 is already very close to 10. If you fill it differently in this way, if you change this to 4s1 and 3d10, it turns out this structure has lower energy, because now rather than having 9 electrons in D, you have 10, which is fully filled. That means all 5 d orbitals are filled with electrons. So in this case, the total energy is actually lower. So this, for the energy for this combination is lower than the other combination. All right. So the correct one actually turns out to be C. We have a similar situation. All right. For example, we have a chromium which has 24 electrons. So when you do that, you have a 1s2, 2s2, 2p6, 3s2, 3p6, and then the next thing you do 4s first, right? 4s2, now 3d, it would be 3d4. So if you write it, you might think this is correct, but similar to what you see for copper, which you get the first theoretical electronic configuration wrong, then actually the correct one should be not, rather than 4s1 and 3d4, you have 4s1 and 3d5. So what? Oh, basically, when you look at that, D subshell has 5 orbitals. 4 is very close to 5. Remember, when you fill the electrons into d orbitals, you singly fill out each orbital first, right? So if you fill the 5th one in, d orbitals will be totally symmetric. So it turns out the bottom combination has a lower energy than the top one. Okay, so this one is wrong. The bottom one is correct. And the first portion, as I said, that is actually, sorry, it's not a neon. This is actually argon. Okay, argon has 18. Neon has 10. Okay, all right. So it's argon rather than neon. Okay, all right. Did not even notice that. Okay, let's continue. How many unpaired electrons are in iron atom? So let's do iron, folks. Okay, all right. Iron. Look at your periodic table. You'll find that iron has 26 electrons. You do this one by one. 1s2, 2s2, 2p6, and 3s2, 3p. Remember, after 3p, how many d? What orbitals are you going to fill in first? Oh, it's 4s, not 3d. Okay, it's 4s2. Then you counted. This is 20. Okay, you need 6 more. That means after 4s, it's 3d. So you do 3d6. Oh, how many unpaired electrons do you have? And remember, the inner electrons, they're all paired up, because all filled up, of course, they're paired up, right? So it's only the last subshell that you fill in can have the unpaired electrons. So let's do 3d only, all right, using the orbital diagrams. D has 5 orbitals, 5 boxes. So you have 6 electrons filled in this 3d orbitals. So you have the first 5 will fill in the d subshell singly in the same spin. The 5th one comes in, the 6th one comes in, it has to be paired up. So you will have actually how many electrons? 4 unpaired. Did you see that? It's 4 unpaired. So that's why C is correct. All right? Okay. For the noble gas core notation, we actually talked about this already. But let's just go over this for one more time. All right. For example, for sodium, sodium has electronic configuration. Actually, this is not represented correctly. This is 3s1. And magnesium, Okay, all right. So when you write this thing, you do notice that the previous row, hey, look at your periodic table, all right? Because sodium is actually in the third row. Now, in the previous row, on the right side, okay, the last element is neon. Okay, that's the eighth group, which has 10 electrons. Okay, so you use the previous row noble gas to represent portion of the electrons. So that's neon. And you write neon to represent it. Then you write the rest. This is so-called abbreviated electronic configuration using the noble gas core in the brackets, right? So similarly, you can do magnesium this way. Use neon to represent the first 10 electrons. Now aluminum, similarly. Okay, all right. Look at this example. Actually, it should be quite straightforward for you, but we're going to use this example to talk about what is the core electron, what is the valence electron. Basically, the valence electron is the electrons in the outermost shell. Hey, what is shell? Still remember? Shell means the number 1, 2, 3, 4, 5 before the SPDF. Okay? All right. So when you look at the silicon, when you write the electronic configuration, all right, what is the largest shell number? It would be number 3, right? So everything in the outermost shell, you call that valence electrons. Okay? So everything that is not valence electron, we call that a core electron. So how many valence electrons do you have for silicon? Oh, it's 4. 4 valence electron, VE, right? How many core electron? That would be 10 core electrons you see over there. All right. For selenium, the example which we already worked on, when you write this thing, look at that. It's slightly more confusing because 4s is embedded in between the 3p and 3d. So the outermost, you have n equals 4. You would have 4s2 and the 4p4. So you count both of this together. That will give you 6 valence electrons. Everything else are considered as the core electrons, which is 28. Okay, all right. So now let's summarize everything and look at that in the periodic table. When you write the electronic configuration for the outermost shell or the important shells, okay, you will notice that, for example, for group 1A, you all have S1. Did you notice S1? 1s1, 2s1, 3s1 for the outermost shell. And for 2A, you have a 2s2, S2, 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 S, the outermost, right? So you do see a pattern over there. When you look at 3A, for example, you have, after you fill in S2S, then you have a 2P. After you fill in 3S, you have 3P. So they all have NS2 and the NP1 electronic configuration. Did you see that? And when you pay attention to this, you also notice that the outermost shell has 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. Then the second one has 2. The third one has 3, 3, 3. Did you see? Now you look at 6A. Oh, 2 plus 4. Oh, that's 6 valence electrons. Oh, 6, 6. You look at 7 for 7A. So basically what this tells you is the number of valence electrons for the main group, which is the ones that stick out, okay? For the main group elements, the number of valence electrons is equal to the group number of that column. Of course, we have one exception. Look at that. Helium is the exception. Helium only has 1s2 as the valence electrons. That's 2 valence electrons, although it is sitting in 8A. All right. So this information we just talked about is summarized over here. Okay. You can read it on your own. All right. Now let's look at the next question. How many electrons are in arsenic atom? So first, of course, you're going to find arsenic in your periodic table. And then let's go to the periodic table. Arsenic, As. Okay, how many valence electrons does it have? Arsenic is a main group element. The number of valence electrons equals the group number in the AB system. So arsenic would have 5, let me rewrite the 5 valence electrons. Okay, so arsenic is number 33. That means you have 33 total electrons, out of which 5 is the valence electron. So 33 total minus 5 valence electrons, then you have co-electrons. That would be 28 co-electrons. Okay, 5 is the number of valence electrons, which is the same as the group number. So hopefully by now you have a complete and full understanding of how to do the electronic configuration. The reason we can do electronic configuration is because we know several rules. Let's summarize it over here. The first, electrons will fill the lowest energy state first. That's the lowest energy principle, or sometimes we call it Aufbau principle. Okay, that's the first rule. You fill in the lowest energy state first. Okay. Second, we know each subshell contains certain number of orbitals. S contains 1, P contains 3, and the D would give you 5 orbitals, and F is 7 orbitals. We also know in each orbital you can only put 2 electrons max inside. So S can take 2 maximum, and P can take 6, D 10, F 14. And next, we also know Hund's rule, which tells you for the orbitals with the same energy, you fill in each orbital in the same spin first before pairing up. We also have a special case which tells you if, for example, if you have something like a 4s1 and three D10, which is the correct one. This is the exception, okay? We summarize on this page. Yeah. That's correct. But if you have 4s2, 3d9, that's actually wrong. Okay, so this is actually for copper. For copper. We went over that example, but I'm going to put it over here in the summary. All right. Okay, so with all this information of how the electrons are arranged in the periodic table, we can go back to the original question. Why some elements are very reactive like hydrogen, some are so inert. All right. Some more observations. Sodium tends to form a Na+. Why not a Na+2? Why not to do something like this? Okay. Why fluorine do F-? Why not F3-? Okay. Right. So why is that? And we also know some elements are metals, some are non-metals, and the metals like to lose electrons, as we learned in the previous chapters. But why is that? Why non-metals like to gain electrons, metals like to lose electrons? The reason is because if you have an electronic configuration that is the same as the noble gas, then you are very stable. So when sodium loses 1 electron, sodium has 1s2, 2s2, 2p6, 3s1. Hey, when you lose this electron, it becomes 1s2, 2s2, 2p6. Oh, that's the same as neon. Noble gas configuration. Did you see that? That's why you want to lose 1 electron, because if you lose 2, it would be different from a noble gas electronic configuration. Okay? All right. So let's go into the details of some of the characteristics. For example, the charges of some of the elements can carry. For example, in group 1A, according to what we just learned, 1A usually carries +1 charge. And 2A, it carries +2 charge. Why? Because when sodium loses 1 electron, it becomes the same as neon. Okay? When the potassium loses 1 electron, it becomes K+. It becomes the same as the electronic configuration, same electronic configuration as that of argon. Okay? So it's the same way for magnesium, for calcium. That's why for group 2A, you lose 2 electrons, become +2 charge. Right? Similarly, if you are already close to the 8th column, right, like fluorine, if you gain 1 electron, you will become the same electronic configuration as that of neon. So that's why you want to gain 1, not gain 2, because it would be too many. It will be 1 more than neon. That's why you gain 1. But if you're 2 columns away, like a 6A, you gain 2, then you become the same as the noble gas. For example, O2- would have the same electronic configuration as neon. Okay, so that's how we can predict what kind of charges some elements could carry, and we do have rules. The metals like to lose electrons, and non-metals, they are closer to 8A. Non-metals like to gain electrons. All right. Let's go into some other predictive power of periodic table. All right. So one periodic trend we know of is the atomic size. For the atomic size, when you look at the periodic table, so basically in the same row across the same period or the same row, okay, from left to right, atomic size will decrease. Okay, in the same column from top. So basically in the same row, it decreases from left to right. In the same column, it increases from top to bottom. So if you have a periodic table, which looks, I mean, roughly like this, okay, yeah. So from left to right, the size decreases. And from top to bottom, it actually increases in atomic size. Right. That's the first trend. The second trend, actually, we just talked about. Down the column from top to bottom, atomic size actually increase. Okay, and this can be explained by the electronic configuration. All right, we have a few more that you need to pay attention to. We just talked about atomic size, trend, and ionization energy. What is ionization energy, by the way? Ionization energy means the energy it takes to remove 1 electron from the neutral atom. Okay, so if you have higher ionization energy, that means it's more difficult to remove the outermost electron from the atom. So the trend is opposite compared to the atomic size. From left to right, actually, you will have the first ionization energy. You can emphasize it's the first electron. So first ionization energy, first IE. Okay, actually increase from left to right. From top to bottom, it decreases. For metallic character, what is a metallic character? Which means, do you behave more like a metal? What do you mean? Metals like to lose electrons. Metals can shine. It's lustrous. All right, that kind of stuff. Okay, that's the metallic character. From top to bottom, actually, when you from top to bottom, the metallic character increase, but when you move to left to right, actually, metallic character will decrease. Okay. For the atomic size, look at this table. Apparently, when you look at that from across the row in the same period, yeah, look at that. The size decrease from left to right. And from top to bottom, it actually increased. Okay, so that's what you can see for atomic size. One thing that can save you a lot of time is, for example, if I just get rid of all the real sizes over here, I ask you to compare, for example, let's do chlorine. Okay, now I have phosphorus. I might have tin over here. I ask you to arrange these three atoms in the increasing atomic size. So we're going to do, there's one trick that you can do. When you are closer to the right top corner, this corner, it gives you the smallest atomic size. If you're closer to that corner, that means you have smaller size. When you are closer to the bottom left, that's the largest atomic size. So you can circle chlorine, phosphorus, and tin in the periodic table. That's my phosphorus, okay? That's my chlorine. Then you have your tin over here. Where's the tin? Tin is over here. Okay, so which one is closest to the largest corner? Oh, that's the largest corner. That's the smallest corner. So if you want to increase the atomic size in increasing order, it would be, remember, right top is smallest atomic size. So it's closer to that corner. That's the smallest size. Now, a phosphorus has a little bit larger, and tin would have the largest atomic size. That's how you do it. Actually, we could do this similarly for the first ionization energy and the metallic character. You do see one more thing we included, which is so-called electronegativity. Okay, we put it over here, but we're not talking about it. We will, though, in a different chapter, electronegativity. Okay, so basically for this size, this is largest atomic size, and this is the most metallic character, stuff like that. Okay, caricature. We get caricature. That's a lot more than you need. Okay. All right. So I'll give you another example. For example, let's just look at the next example. Okay. Arrange the following elements in the order of increase in ionic energy. First thing, hey, write down what you already know. Which one has the largest ionization, first ionization? Hey, this is the largest first ionization energy, okay? And this is the smallest first ionization energy. Hey, circle silicon. Where's my silicon? Where's my fluorine? That's my fluorine. Where's potassium? Find your potassium. Magnesium. Then where's my sulfur? Oh, where's my sulfur? So basically, the closer the element is to the largest corner, then you have a larger first ionization energy. The opposite is also true. In the order of increasing, so just basically, this is the smallest corner, just write from the left bottom to top right. So smallest, second smallest, then you keep going. It's arranged. It's actually arranged for you already, isn't it, right? So potassium first, then magnesium, potassium, magnesium, potassium, magnesium, potassium, magnesium. But the next one is silicon. Oh, silicon next. Then you have sulfur. Where's my sulfur? Sulfur, silicon, sulfur, fluorine. Oh, so D is the correct answer. All right. Which of the following atom has the greatest metallic character? So remember the left bottom. This is the most metallic. Okay. Or biggest metallic character. And the least is on the right top corner. Okay. So you just basically circle a chlorine. Then here's the carbon, here's the aluminum. So where's my chlorine? The first one, that's my chlorine. Now tellurium. You also have an indium. Then you have carbon. Then what else? Aluminum. So which one is closest to the left bottom corner? Oh, look at that. That's indium. So that one has the greatest metallic character, or it's most metallic. So indium is the correct answer. Which of the following statement is true of Bohr model of the atom? So what is orbital, orbits. Remember, orbits is what Bohr's model talk about. Bohr's model. Okay? Orbitals is quantum mechanics. Right? And orbitals are the probability map. Orbits are not. So let's look at each choice. A, an orbital, that's wrong because it's not about Bohr's model. Second, it says an orbit starts well, is a probability map. No, orbits are not a probability map. Orbits actually describes exactly when and where you can find that electron in Bohr's model, which is totally different from quantum mechanics. So orbit is correct, but probability map is wrong. So an orbit is the electron's circular path around the nucleus. That's exactly what an orbit is in Bohr's model. So C is the correct answer. Look at the next one, which is a related question. Which of the following statements is true or are true about quantum mechanics model? That's exactly the same. First, it's not going to be an orbit. It's orbitals. What is orbital? Orbitals. So basically, look at orbitals in this model have different shape. Yes, they have different shape. Yeah, that's correct. We do know s orbitals have a spherical shape like a ball, and the p orbitals like a dumbbell, and then you have d orbitals. Looks like most likely like four balloons tied together. Maybe looks like this is d orbitals. Okay, all right. You also have f orbitals, so they do have different shape. So A is correct, but anytime you see statements like E, you got to keep looking because E says two of this are correct. Do we have two correct? So look at D. An orbital is the probability map showing the likeliest location of electrons around the nucleus. This one is also correct. For this reason, you pick E as the correct answer because both A and D are correct statements. All right, this lecture is kind of video lecture is kind of long, but hopefully you have enjoyed it. If you got any questions, please feel free to let me know. By the way, if you've been wondering why do I keep looking on the right side, it's because on the right side I have the screen. I want you to have a look at here, so I can write on the screen. That's why I keep turning to the right side when I record this video. All right, if you were wondering. All right, have a good day.